Hello everyone, my name is Andrew Estornell. I'm going to be presenting the paper Group Fair Classification with Strategic Agents. So before we get into the ways in which strategic agents end up impacting group fair learning, we'll just look at the simple example of lending so that we can see the type of problem that we want to look at. So in lending, you typically have applicants, and maybe these applicants fall under two groups, blue and green. Each applicant submits an application to the bank, and the bank uses some algorithm or automated decision-making system to make a binary decision, approve or deny, on each applicant. And in these types of binary decision-making systems, a simple way to define group fairness might be to measure some type, or to ensure that some type of measurement is roughly equivalent between the two groups. So here in this example, we're saying that the algorithm F is beta fair if the percent of blue applicants and the percent of green applicants approved is no greater than beta. And so more generally, you could just define some unfairness function that's a function of the predictor F, the features X, the label Y, and the groups G. And we would call a model beta fair if it's the result of some type of loss minimization subject to an unfairness constraint. The unfairness can't be more than beta. And this is in contrast to, say, a conventional or fairness agnostic model, which is just doing loss minimization. And so what we'll be interested in is looking at the relationship and the relative fairness between these two models under strategic behavior. And in particular, we want to ask, how does strategic agent behavior affect the fairness of FF and FC? And we'll be interested in how the relative fairness between these two models changes when agents behave strategically. And so next, we'll just set up what we mean by strategic agent behavior. So again, as an example, we might have applicants, and maybe an applicant has this application with $2,000 of assets, $50,000 of debt, and they know that the bank will deny them if they submit this application. So they falsify or manipulate their application to over-report their assets and to under-report their debt. And the hope is that by doing this, they go from being denied a loan to being approved for a loan. And so just to give a mathematical definition for this, we say that for a given agent with true features X, which is originally denied, f of x equals 0, the optimal manipulation is given by the manipulation that minimizes some manipulation cost function subject to the manipulation, x prime, being positively classified. And here we'll say that an agent will manipulate if the cost is not too great. So there's some manipulation budget, and as long as the cost is less than that manipulation budget, agents will manipulate. And in our paper, we study two common types of manipulation cost functions, the first being so-called feature monotonic costs, which are monotonic in the LP norm between the true features X and the manipulated features X prime. And the other type that we study is so-called outcome monotonic costs, which are monotonic in the conditional probability of these features. And the first type, feature monotonic costs, captures the idea that larger lies, larger manipulations are more costly. Outcome monotonic costs capture the idea that better lies or better manipulations are more costly. And in this paper, we propose a definition called a fairness reversal. And here, a fairness reversal is an event that occurs between FC and FF when strategic behavior causes the fair model FF to become less fair than the conventional model FC. So we're effectively saying that the relative fairness of these two models has swapped, in that under truthful reporting, FF is more fair. Under strategic reporting, FC is more fair. And so just to give kind of an example of this, we are interested in asking not just do fairness reversals occur, but also why do they occur? So we'll just take a look at kind of what we mean in practice by a fairness reversal. So this is an example on the community crime data set, and we're measuring unfairness here in terms of positive rate difference. And what we can see is that when the manipulation budget is 0, meaning that all agents truthfully report, the fair classifier is more fair than the conventional classifier. However, at about manipulation budget 1.2, we see that the two models have equivalent fairness, and then beyond this, we actually see that FF becomes less fair, meaning that a fairness reversal has occurred for these manipulation budgets, meaning, again, that the relative fairness of both models has swapped. And as I said before, in this paper, we're interested not just in outlining that fairness reversals occur, but why they occur from both an empirical and a theoretical perspective. And just to give a bit of intuition, what we found is that by analyzing the decision boundaries of these classifiers, we're able to come up with conditions under which fairness reversals will occur. And in particular, what we found is that when fair classifiers achieve their fairness by being more quote unquote selective, meaning that they have a lower positive rate than their conventional classifier, we see these fairness reversals occur. And so the notion of selectivity is a little bit more subtle than just the positive rate of the classifiers, but it can be roughly interpreted as this. And kind of the intuition is that a fair model can achieve its fairness in one of two ways. It can typically include more positive examples from, say, the disadvantaged group, more positive predictions, or it can exclude positive predictions from whichever the advantaged group is. And you can see that when the fair model is excluding examples, it's getting more selective, meaning that it's decreasing its positive rate compared to the conventional classifier. And what we find is that when models are inclusive, when fair models are inclusive, meaning that they make more positive predictions than their conventional counterparts, fairness reversals do not occur. However, when these fair models are more selective, that is precisely when we see these fairness reversals occur. And from an empirical perspective, we observe this quite frequently. And from a theoretical perspective, we have a slightly more strict definition of selectivity, which is simply that the positive decision boundary or the positive predicted region of the fair classifier is a subset of the positive predicted region of the conventional classifier. When that occurs, we say that FF is more selective than FC. And we have several theorems, which I'm kind of wrapping into one informal theorem here, which says that fairness reversals occur when the fair classifier is more selective. So essentially we're saying that when the positive predicted region of FF is a subset of the positive predicted region of FC, a fairness reversal will occur. And we also noticed and then theoretically characterized the fact that accuracy reversals also occur under this condition of selectivity, meaning that not only does the fair model become less fair, but the accuracy maximizing classifier actually becomes less accurate than the fair model. And so we're seeing that kind of almost the relative function of both of these classifiers has swapped, where now the fair model is the more accurate one, and the more accurate model is now the fair one under strategic behavior. And just to give a bit of intuition as to why selectivity would lead to this, we can look at just single dimensional predictions. So here we're looking at kind of a classic example on the law school data set. We're simply using student LSAT score to predict whether or not they will pass the bar exam. And what we're seeing on the x-axis is a threshold, just simply a threshold classifier. And the error and unfairness of that threshold classifier is on the y-axis. And so what we can see is that both of these functions are relatively unimodal, error and unfairness, with respect to the threshold. And so what we could say is the conventional threshold, meaning the accuracy maximizing threshold, is going to be the threshold that's at the minimum point of this blue line, which is the black line corresponding to theta c. That's the optimal conventional threshold. And then the fair threshold is going to be the accuracy maximizing threshold that doesn't have too much fairness or too much unfairness. And so here we're just saying that the allowed unfairness in this particular example is 0.15. And so that ends up corresponding to this particular threshold. Now, when agents behave strategically, because agents are only ever trying to go from being negatively classified to positively classified, manipulation effectively corresponds to shifting these thresholds down or decreasing these thresholds on the true distribution. So when agents manipulate, when the population manipulates, these thresholds effectively decrease. And what you can see now is that as this manipulation grows, these two thresholds are traversing the same error and unfairness curves. And it ends up being the case that when the fair model is more selective, meaning that it has a higher threshold, right, that corresponds to greater selectivity in this case, then as we go back towards a threshold of 0, the fair classifier, this fair threshold, is actually going to hit is going to hit the maximum possible unfairness, meaning this peak. And while that's happening, the conventional classifier is decreasing in fairness. So we can see that as these two thresholds traverse the same error and unfairness curve, the relative unfairness swaps. And also we see again that the relative error of these two also swaps. And so in this one-dimensional example, this is precisely why selectivity of the fair classifier leads to fairness reversals and accuracy reversals. So just in conclusion, we saw that strategic agent behavior can lead to fair models becoming less fair than their fairness agnostic counterparts. Fairness reversals are also accompanied by accuracy reversals, again indicating that under strategic behavior, the functionality of these two models has fundamentally swapped on both the dimension of accuracy and unfairness. And we also saw that classifier selectivity plays a crucial role in fairness and accuracy reversals. And again, we provide not just empirical observations that this is the case, but theoretical justifications for why selectivity plays a crucial role in these fairness reversals. So thank you all for coming and listening to this talk. And if you want to check out the full paper, again, it is Group Fair Classification with Strategic Agents, and it is number 179.